Ok, we are live. Joia. Bom, muito boa tarde a todos. Vamos dar início à sessão de palestra do workshop de tese e dissertações em computação. E é uma convidada internacional, então nossa palestra vai ser nossa sessão vai ser conduzida em inglês. Good afternoon, everyone. I'm very pleased to welcome Shazia Tabassum from Portugal in our workshop. Shazia Tabassum is a researcher at the Laboratory of Artificial Intelligence and Decision Support, LIAD, INESCTEC Porto. She obtained her PhD in Informatics Engineering from the Faculty of Engineering, University of Porto in Portugal. She also holds the degrees of bachelor's and master's in computer applications from India. Over the past 8 years, she made significant contributions to research in the diverse areas of data science, machine learning, social networks, data visualization, and explainability applied in the domain of transport, retail, telecommunications, tourism, and social media by working in European research projects and industry collaborations. She authored a number of publications, including book chapters, high-quality journals, and conference proceedings at notable venues IEEE, Wiley, Springer, Cambridge, and ACM. She served as a reviewer in several index journals, conferences, and also as a speaker or co-chair of the special sessions, workshops, and conferences. And today, Shazia will talk about anomaly detection and explanation. Shazia, we are very happy in having you here today. On behalf of the organization committee, I would like to say thank you. So, is with you. Thank you very much.
Thank you, Fabiola. Thank you for the very nice introduction. And I would take this opportunity to present the work that we are carrying out in our lab in the Laboratory of Artificial Intelligence and Decision Making at INESCTEC, which is located in Porto, Portugal. So the work here now I will explain about anomaly detection and explanation, and then I will present an example case study to elaborate the topic. So explanation nowadays is a buzzword. Everybody will be hearing this about explainable AI, which is required nowadays because of the increasing complexity of models. So we will go into that further later, and first we begin with anomaly detections, like what is anomaly. So let's start with the basics, like what is anomaly. Anomaly is something that deviates from the normal or expected behavior. So they are also called outliers or exceptions, etc. But outliers can be anomalies. Anomalies are especially the ones that are unexpected and that are not desired. They usually occur in the events such as frauds and failures, like credit card frauds, where there are anomalous patterns and fraudulent patterns in the transactions, and those are anomalies that we can detect. So there are how is the detection of anomalies depends, the task depends on the availability of data, and in the availability of data, do we have the labels available or not? If there are labels available, we go for the supervised anomaly detection. And if there are only labels available for the normal class and we do not have labels for the fraudulent class, like which points or which data points are fraudulent or which patterns are fraudulent, we do not have information of that, we go for semi-supervised anomaly detection. And most of the times we don't have label instances. We do not know how the malicious users behave or what kind of techniques they are using to intrude into the systems and do some attack the systems or such kind of behaviors. So most of the times we don't have labels available for that. So then we have to go for unsupervised anomaly detection. This is one of the most common technique that you use for anomalies because of the lack of labels. So now let's go to see how we detect anomalies. We go for the basic technique, that is the statistical technique for box plots used for detecting anomalies in univariate data streams when you have one feature, or you can also use for more features, but you have to use it on on the individual features independently. So in the box plot is very simple. We understand the range of the values, and the values that are exceeding or beyond the third quartile, somewhere beyond the third quartile, are considered as outliers or in anomalies in another case. So this is very powerful tool which is still used because of its it is easy to visualize the distributions and easy to detect the anomalies, and it is simple and we can interpret it easily and explain it easily. But there are limitations that we cannot use box plots for all the scenarios. As I said, it is limited to the univariate data, and we can use it for multivariate, but then it is independently on features and we will miss the relationship between the features. So and then also it is not very effective on long tail distributions. As you can see in the figure, we have a long tail distribution and there are a lot of anomalies, and we have many more anomalies than in the normal data. So this is one of the example, and also it uses box plots uses the fixed thresholds. That is also one of the limitations. So let's see an example of how we use the statistical technique for multivariate distributions. For multivariate data, we can use Mahalanobis distance. It is another robust distance measure that considers multivariate data. And for a vector of points and the mean and a covariance matrix of the features, with this equation below, we can find the distance between the points. And here, for example, this figure represents the points and the distance between them. And the red line is the threshold that we consider in this example, or it is derived from this data set. So the points below this threshold are considered as anomaly points. So, but again, we have this drawback of having fixed threshold and loss of accuracy in these kind of models. And so we, to have better accuracy nowadays, we use more complex models such as neural networks. Neural networks, we have a set of inputs and something happens inside the black box, and then we get the set of outputs. But we do not know what is going on inside the black box. So we need, so that is also a challenge with these kind of black box models. We have increased accuracy, but we have some challenges that are associated with these kind of black box models. That is, there are a large number of parameters and there are intricate mathematical structures, and we cannot interpret what is going on, and we do not know if the output is based on some biases inside the data or input, and we cannot calculate or evaluate the fairness of the model. And if we do not have interpretability and transparency in the model, it leads to mistrust, and also who can we account for the model, like for the faults or for the errors in the model, for the false positives. No one can take the accountability for having the wrong predictions. And there is also concerns about security and the regulatory issues. So there are these challenges and many more others that are associated with these kind of black box models, such as neural networks that I showed. For example, if we have a criminal justice system and the black box model, the neural networks gives us an output that the users, or is a criminal, but it doesn't explain why is he the criminal. What are the features that are showing him as a criminal, and how we can understand that. And if it predicts, for example, in another scenario where we have to detect the failures in the machines, and it detects the failure accurately, but where is the failure occurring, in which component of the machine, and why is it occurring, what is the values, or what are the features that are contributing to that effect. So these are the challenges that are associated with these black box models. So therefore, the explainable AI comes into the picture. What is explainable AI? Explainable AI is to explain the predictions made by the models. Why are we getting those predictions? What are the features that are contributing to those predictions? And what are the coefficients in linear models? And why are we going to take those decision rules? And so it is kind of explanations that we give to explain why are we getting that output from the given input. With the help of this, we can also debug the algorithms, or we can also find the biases in the data. Like if there is a bias in the data and we are getting certain output, if with the help of explanation, we can understand why are we getting that certain output. So the explainable AI is nowadays very important because of the complexity of models. So now, if we don't use the black box models and we use rule-based classifiers for explanations in the supervised learning scenarios, where we have the labels available, we can extract the rules that explain the classification. For example, here, if the height is greater than 5.9 feet, then the algorithm considers it as a male. And then if it is not, it goes to another leaf where the weight is less than or equal to 150 pounds. It's considered as female, and that considers the foot size. So from this kind of decision trees, we can generate rules that make us understand why is the algorithm giving certain output. But this kind of rule-based classifiers, there are some limitations associated also with them, because the rules are not exhaustive. There are limited set of rules, and if we do not have a rule for a, for an example, if we do not end up deriving a rule for an example, then we we allot a default class to that example. So it is also sensitive to noisy data. If there is noise in the data, if there are outliers in the data, the structure of the decision tree changes. And it is also biased to dominant classes. In cases of anomaly detections, we have a dominant class that is a normal class. So it is also, it decreases the accuracy in those type of scenarios. And then also when we don't have labels, we have to go for the unsupervised learning and to increase it. So here we see that how the learning performance and explainability is affected. When you have high learning performance, from the research we see that the deep learning algorithms give high learning performance, high accuracy models. And the models such as decision trees, they are good in explainability. We can explain the models with the rules, but they have low accuracy. So there is this trade-off now, because we are not having so many techniques for so many approaches or mechanisms for explaining the models. We have this lack in explainability for the black box models, and we have low accuracy in decision trees, which is obvious in most cases. And then it is another, we can see the SVMs having less accurate, more accuracy but less explainability. So this is a trade-off between the explainability and performance of models. So how do we use a neural network for unsupervised learning or detecting anomalies? So the most common neural network that is used for detecting anomalies is autoencoders. Autoencoders are also used for decreasing the dimensionality reduction. So it works by you have some input to the autoencoder, and the encoder layer here, it performs some calculations to learn and compress the input data into some representation that is reduced. And then using this representation, it reconstructs the input, and the difference between the reconstructed input and the original input is considered as a loss function or error. It is used to detect the anomalies. So we present here a case study where we use autoencoders to detect anomalies, and then we will learn how to also explain them. So we have a case study here. We have data from the metro rail, and the problem is to detect the fault in the air compressor unit inside the metro train, and we have to detect it to at least 2 hours before the failure occurs. Because after 2 hours or after some time, if we don't detect it on time, then the train stops, and it will cause inconvenience to the passengers, and it will be not feasible to take the train to the service station right on time. So we have to find this fault before the failure occurs. So the task is to detect the anomalies in the signals from this air production unit and explain them so that the employees from the metro rail department can understand which component is the failure occurring, and so they can take the train to the service station before the failure occurs, causing and it decreases the loss to them when the train goes to the service station on time. So the data set in the data set we have these features that are some of them are analog and some of them are digital, and we have around 6 months of data and 10 million data points from the 1st of January to the 24th of February. That is where the first failure occurred, and the train has to go to the service station. We consider the data, that period of data for testing. So when the first failure occurred, the first failure is the air leak, which occurred in the air dryer component of the air compressing unit, and it started on this date and ended on this date. And there is another failure. There are three types of failures that occurred, and we know when these failures have occurred in the data. We have the information. So the task is to find the failures before these actual failures occurred. Therefore, we used the LSTM autoencoders because we have the sequential data. The data occurs as a stream of signals. When the train is running, we keep on getting the signals from the train that are logged on the database, and we have to use that streaming data. Therefore, LSTMs are good in capturing the long-term dependencies in the sequential data. They produce the compact representations of the input stream and then produce an output stream. So therefore, we consider LSTMs and club them with autoencoders to detect anomalies in the stream of data. And now we detected the anomalies. We considered the root mean square error and a threshold of similar to the box plot, and then we considered a smoothing function on that to get the anomalies. Now we have the anomalies and that have occurred, that show that the failure occurred. But how do we explain this? How do we explain these anomalies to the concerned departments? Because the end users or the stakeholders, they do not have all the knowledge about the calculations happening in the black box model. So we use here Shapley additive explanations. It is a method that you use to explain how are the features affecting the model. So with the use of SHAP, we increase the transparency and interpretability of our model. But the SHAP does not evaluate the quality of prediction. It does not have to do anything with the prediction, anything to the quality of prediction. It does not change the predictions. It only explains you why we have resulted in this prediction and what features have affected these results. And the SHAP values also, they have one more advantage here, that they give local explanations and also global explanations. Global explanation is based on the overall performance, overall importance of features, and the local explanations are per observation. So let us see how the shape values explain our models, our predictions. So this is an example of the shape plot illustration. And these are the features that we generated, and based on the analog and digital features we generated some more features. By dividing the signal into bins, we have generated some more features. So on total we have around 50 features, and we use those features for predicting anomalies in the model. And the shape plot shows that what is the expected output and what is the predicted output, and what is the contribution of each feature to the output. It ranks the features according to their contribution. So the most contributing feature here is T1, and it explains that we have the failure or problem, or it is normal, but it is the T1 which is contributing the most. So when we have some anomaly detected, we have something like this, where some features are where the predicted value is very high than the expected value, expected prediction. Here the base value is very less compared to the predicted value. So we can see that this is caused by this feature or this component, that is T1. And then we see that how the over time how our Shapley plot changes with the values over time. So this is how we see there is some large difference in predictions is long before the failure occurred, and then we have some normal patterns right before the failure. We have some normal patterns because the compressor works hard to overcome the malfunction in certain components, and then the compressor works hard and gets the train back to system back to normal. So right before the anomaly we have some normal pattern, and this red plot shows when the anomaly occurred or when the failure occurred. So right before failure we have some normal pattern, and then sometime before failure it shows, I'm going back in these plots, and sometime before failures we have a normal pattern before failure, and then we have some abnormal pattern here sometime with a gap before the failure. So we can detect when we see abnormal patterns, we can detect there is the anomaly, and it explains us which features are contributing to this prediction. So they can look for these components which are generating these features. So that is how we can explain the anomalies. Using Shapley values, we have also some other methods for explainability. And then finally, what we have learned from this is how we can detect anomalies in univariate and multivariate data, and how we use explanations from rule-based classifiers, and then we detect anomalies, and give some explanations, use SHAP for explanations in unlabeled data using black box models, and how, and also we think that machine learning models are getting more complex, so there is exigency for more explainable models. And having this explainable AI enhances the transparency, accountability, and fairness and trust. And to overcome these limitations, we need more human in the loop systems where humans coordinate more with these AI systems, or we include expert knowledge in these systems and understand these black box models. So I have some references here that I have chosen in the presentation, and these are our works. And you can find the data set here of the metro train. So thank you very much. And if there are any questions, I'm happy to take.
Thank you, Shazia. That was a very good presentation. Congratulations. Really impressive work with a topic that has many applications in the real world. Um, Let me switch to Portuguese a little bit. Pessoal, se tiverem dúvidas, podem colocar no chat, por favor, que nós faremos as perguntas à Shazia. Okay, so let me start with a first question, Shazia.
Mm-hmm.
First of all, I love the figure about learning versus explainability.
Mm-hmm.
Very insightful. I'd like to know, is there some difference between anomalies and outliers, or we can consider as the same?
Outliers are usually the outliers can be anomalies. There are both of them are something that doesn't conform or that deviates from the normal behavior. Some data points or patterns that are not normal, we consider them as anomalies or outliers. Usually, they are used as interchangeable terms. But the outliers can be anomalies, but anomalies we call them specifically in some contexts, like when they are not uh, in some contexts like failures, frauds, and errors. In these contexts, we call them anomalies. They're also a kind of outliers, but we specifically call them anomalies in these kind of scenarios when they are unexpected, something that goes unexpected, and something that are undesired, some catastrophic events or something. We get those outliers. We call them anomalies. Just to be more specific with the context, we call them anomalies.
Okay, thank you.
Here we consider the failure as the example, so we call them as anomalies in this context. Mhm.
Another question, Shazia, in the case study
Mhm.
about our production in Metro, you handle the data as a string, right?
Mhm. Yes, yes.
And you use LSTM architecture?
Mm-hmm.
Yeah.
Yes.
And besides the LSTM architecture, did
Mhm.
you have some kind of forgetting factor? I mean, or every data coming was important to the model?
Yes, yes. We considered window. We consider the sliding windows in
Ah,
the screen, and the window, the length of the window, I'm not sure, but we considered the sliding windows
Okay.
over the stream of data.
And as you had to predict in at least before 2 hours of the event, the model, what you can tell us about the execution time of the model. Uh,
Mhm.
did you have some performance problems or something like that?
Okay, yeah, this is an issue also with these complex models. They consume more time as the complexity increases. Yes, we had this problem with the complexity of time, but we were not predicting in real time, so we did not consider that issue now. But yes, the model takes a long time to be executed. But I think because we are executing on the whole data set, then so for every window period of data, I think it should not take much time.
Okay. And so you said in the end the data set is open?
Yes, yes, it is available. I think we have one more link updated, but you can also check here the benchmark data set for predictive maintenance.
Nice, good to know. Just to say feedback here in the audience loved your pictures, your tables, and yes, the explainability is very clear. So beautiful pics, right? Another question is um, now I'd like I when you said about uh, you talk about anomalies, I've been thinking uh, topic models can be used to detect anomalies.
Mm-hmm. Mm, topic models such as
S- Yeah, such as in text to
mhm,
mine context, such as LBA and so on.
yes, yes, we can detect anomalies also in the data, and also we use autoencoders also for generative models also. Uh,
Okay.
so autoencoders are used in this kind of task also.
Mhm.
There, I think there are works in this area also.
Yeah, and okay. Another question, and now talking about complex networks, we can detect anomalies in complex network. Does it make sense maybe to detect anomalies in edges or nodes?
Mm-hmm. In images, oh, sorry.
Yeah, in complex networks, in edges or in nodes.
Yes, yes. Anomalies occur in any kind of data. We can detect anomalies in them.
Yeah,
Yeah.
so yeah, so we can
Mm.
detect some anomaly in edges in a complex network, and maybe this we can put some semantic in this edge. For example, we can in a fake news context we could maybe detect anomalies. Does it make sense?
Mm-hmm. Yes. The Yeah, we can. Yes, in the fake news. Yeah, we can find anomalies in that.
Okay, nice. So,
About the relations between these kind of text or documents, considering the relations in the also in the graphs. Mhm.
yeah, okay. So, no more questions in our stream, and we could talk more about anomalies. This necessary topic is a foundation for many applications. And so, but I need to stop this stream. And
Okay.
I'd like to say thank you, Shazia. That was a very good presentation. Congratulations to your work. It was a big pleasure having you here. Thank you very much. Would you like to say some last words?
Yeah, thank you very much also for having me here and giving me this platform to share with the students and explain them what we are doing here and to share this knowledge. And I try to keep the presentation simple and beginning from the basic concepts, so it is easy for everybody to understand who are not from this specific area. So I try to keep it simple. So, and thanks a lot also for having me here.
Okay, thank you, Shazia. I will now stop the stream. Thank